This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hello, everybody, and welcome to the Math Map. We are here on June the 3rd. I'm not really sure how it became June already, but we are going to talk about multiplication, place value, and the distributive law. We're going to break multiplication up into 2 weeks. So we're not going to look at all of the different forms of multiplication this week. We're just going to look at the underlying process of multiplication. And then next week, we're going to talk about arrangement and how we can use arrangement to help us. So fundamentals of math, fundamentals of multiplication is that we have usually two numbers, right? The very basic idea is that we have two numbers that we call factors, and the result is called the product. Now, sometimes we may see 3 times 8, and we call that whole expression a product because we're multiplying, right? It doesn't have to be the final number. It can be the expression of multiplication. When you think about multiplication in the math map, in general, we are going to look at it as the number of hops times the length of the hop, which is the same as the number of intervals times the length of the intervals, or thinking about it as a scalar times a vector. Now, multiplication is commutative and it is associative, which means that I can reverse my numbers, right? And that's what we're going to talk about here in a minute, that I can reverse my numbers and see it both ways. But because as we think about vectors, especially in other dimensions, thinking of it as a scalar times a vector just helps us to sort of keep in order what we're doing. Now, not like what you see on Facebook when people are complaining about homework. We are not there to check that your student has done this in the correct order. So let's look here at the example that I put on the screen where I said that multiplication is equivalent to repeated addition. So in the way that we're writing it, which is generally common when people care about it, this is the common way to think about it, is that 4 times 3 is saying 4 threes, or 3 plus 3 plus 3 plus 3 equals 12. If it was written as 3 times 4, we would be thinking of that as 3 fours, or 4 plus 4 plus 4 equals 12. Notice that we end up with the same result. We get 12, again, because it is commutative. The order doesn't matter if we're just talking about two numbers. At home, right, if you don't want to differentiate between these two, that's okay. If you want to write 4 times 3 and have your students write that is 3 fours or 4 threes, that is up to you. This is, like I said, this is not one of those internet memes where people are complaining because the student didn't do it right, but they got the right answer. That's up to you at home, how you want to do that with your student, right? How detailed do you want to get with your student? But if you look at the work we're doing in the math map, in general, what we're always going to be trying to do is a scalar times a vector. Any questions about that? All right, so let's now just think about last week and the week before. I said take all of your digits from 0 to 9 and just practice adding them, right? If you know the sums from 0 through 9, you're going to be good to know. So this week, we're going to be talking about memorizing 0 times 0 through 9 times 9. Now, that's not to say that I'm discouraging you from multiplying more, right? We know that our students for a memory master work through the 15s, the flashcards go through the 15s. I'm not discouraging you from that. That is a great way to speed up mental arithmetic and become familiar with the numbers. our purpose here is to show you the patterns that underlie the arithmetic so that you can see the minimum things that you need in order to be able to help teach your students arithmetic and help them to see the patterns. So we're being very didactic with the minimum amount so that you can choose how you want to pursue this at home. So I've kind of given it away here, but are we looking for combinations or permutations of our digits 0 through 9? A little review from last week.
Just combinations.
Combinations. And why is that?
Because 3 times 4 is the same thing as 4 times 3, so we don't need to list both of them.
Excellent. Exactly, right? Because it's commutative, we only need the combinations, which is fewer than the permutations. So if I know all of those combinations, I can allow my students to skip count so that they can see the repeated addition in order to calculate the products for the digits. But then we want to move to memorizing those products, right? So we don't want to skip count every time, but skip counting is a way that your students can discover for themselves what the products are. And you can certainly use manipulatives. So if you, last week we talked about having vectors, right, and cutting them out of paper or cardboard, right, that you could take your vectors and say, if I have 3 vectors, and literally lay those vectors out on a number line. Or you could have your students hopping so that they can see what they're doing. Or if you, we used just little squares. And so you could use those as a count. And although they're 2-dimensional, you could say, okay, how many squares do I have in my row? And then how many columns, right? How many squares in my row? And then how many rows do I have? So I would have my columns and my rows. And that would be a 2-dimensional way of exploring multiplication. So let's just take a quick look at what that would look like. All right, so if I said all my combinations of 0 through 9, what would be a way to arrange this? Because remember last week we talked about helping our students to write combinations is a really valuable skill. So where would you start? Would you start with 0? Would you start with 9?
I would start with 0 just because it's smaller.
Okay,
So 0 times 0, 0 times 1. Is that what you're asking for?
Yep.
0 times 2, 0 times 3, all the way to 9?
All the way up to 0 times 9, right? And then what do I not need in this row?
You don't need that 1 times 0.
0 times 0. Yeah, 1 times 0.
So our rows are going to get shorter, right, each time, because now I don't need 2 times 1, so I can start with 2 times 2, and so forth.
So would it be bad, because I'm kind of getting OCD, would it be bad if I put that 1 times 1 under the 0 times 1 and the 2 times 2 under the 0 times, like keep the, you know what I'm
Absolutely.
saying?
Yep.
Okay.
Well, that's what happens, right, when we see a multiplication chart. So what I'm essentially doing, right, is creating a multiplication chart where you have your digits. All right, and so I have my 0 times 0, my 0 times 1, and so forth. And I would skip this one because I already have 1 times 0, 1 times 1. And then you'll see you'll build it up along that diagonal.
So Laura asked, could you use the hundreds chart? So I'm guessing yeah, because it's similar to this.
Not the hundreds chart, because that doesn't show the products. Those are just counts. So I don't think I've got to think about that one. I don't think you'd want to use the hundreds chart because what you're going to see is you're going to have something, I can't remember, but whatever it starts with, then this becomes 10, 11. And so, right, obviously 0 times 1 isn't 10. So but there is a multiplication chart. So there's a multiplication chart on the back of one of the lessons, and that's essentially what we're building here. And so I would do that with your students as I would have them build it because I think that helps them to see the pattern and then show them the multiplication chart and go, look, this is just what you did and this is how it's arranged.
Do we have a chart that has just 100 squares on it that are empty? Is that on something? Maybe
I
like
don't,
that. Oh, Kristen's holding it up
that's on the whiteboard,
on the white. That I was
trivium
thinking it was
table.
somewhere on one of our trivium tables. So that could work as well, just to give you a structure
Yep,
to fill in.
absolutely. Yeah, that or some graph paper or
Right.
yeah, to give you that form. I agree. So then once I've got all of my combinations, now I can go through. And this is where, again, skip counting is that bridge. It's not, we don't want it to become a crutch, but it's a bridge from addition to multiplication. Because if my students can skip count, then I can say, okay, well, what's 2 4s or 2 times 4? Well, I need 2 4s. So I'm going to start at 4, 8. That's 2. So 2 times 4 is 8. And once I get there, that's where I want to make that transition from 4, 8 to 2 times 4 is 8, or 2 4s are 8. Right? That was, my mom grew up in English schools, and that's how they said it. 2 2s are 4, 2 3s are 6, 2 4s are 8, which I think linguistically is easier for our students sometimes to omit the times and just say, I have 2 2s, sometimes makes a little bit more sense. And it's quicker. So just an option there if you're looking for other ways for your students to say that and still pound those pegs in. So that is really your essential memory work for multiplication, right? Just like with addition, I said you really need to know those sums between 0 and 9. You really need to know the products from 0 through 9. If I know the products from 0 through 9, we're going to take a look at place value and see where now I can multiply any numbers, just like I could with addition. But first, let's talk about our integers. And if we think about our factors, when we have integers, each factor could be positive or negative. If we're thinking hops times length of hops, number of intervals times length of intervals, or scalar times vector, we're going to say that that first number is either going to preserve or reverse the direction. And the right factor, the right number, is either going to give me the direction, right? So I'm either going to be going right, or which is positive, or left, which is negative. Okay. If we think about that, when I have a positive times a positive, positive means preserve my direction. And then the second positive means I'm going right. So where do I end up with? I end up with a positive or to the right. If I have a positive times a negative, I'm preserving the left or the negative. So what do I end up with? Left or negative, right? Then I have the negative times the positive. Now I'm going to reverse going to the right, right? So if I started at the right and I reverse it, I end up on the left, which is negative. And then the negative times the negative, if I started on the left and I reverse it, I'm going to end up on the right, which is positive. There's a lot of ways people choose to memorize this, but this is where I think thinking the number of hops or intervals or my scalar, preserving or reversing, helps our students to make sense of why those are swapping back and forth when we have negatives involved. Any questions or anything anybody would like to share about this idea?
I love having these words. I preserve and reverse. I didn't have that. I would say, well, this is the opposite. And well, you switch directions, but it didn't quite explain what we were doing. Yeah. And like when I try to think of -3 times -2, like, so why is that positive? Anyways, this is very helpful. Thank you.
Well, it gives us that idea that each number is giving us two pieces of information, but the information they're giving us is a little bit different in either case.
Yeah, when we
I'm
were doing
really,
addition, when we were doing addition and subtraction, that first number told us where to start,
Mm-hmm.
and that's not happening now. We don't, -3 times -2, we don't start at -3
Where do we start?
at 0, right?
At 0.
Yeah.
Yeah, it's a little bit different. And I hadn't really planned to get into this necessarily, but when we get to the other dimensions and we start looking at the equation of a line, which could also be the equation of a particular point on a line, we're going to see that we're always going to have that our vector or our point, whatever we want to call it, so I'm just going to call it the vector, is always going to have some starting point plus some number of direction vectors. And this becomes this sort of very general equation that I can use in any dimension, right? I can use this in any dimension. But in the first dimension, this becomes, right, that any number could be expressed as a starting number plus some number of hops, right? Well, if my starting position is 0, I'm just left with the multiplication piece, right? So we kind of treat it as just this operation, but that's sort of where it fits into this bigger idea when we're thinking in terms of coordinate space, right? That I could, if you gave me any number, right? There's an infinite number of ways I could do it, but 6 could be expressed as 3 plus 3 times 1, right? So start at 3 and your direction vector is 1, so I'm going to need 3 hops in the positive direction. Or it could have been 9 plus 3 times -1, right? That I started at 9 and I went 3 hops in the negative direction, right, back to 6, right? Is that the number I was trying to get to? All right, so there's all these different ways that I could come up with a number by saying that I started here and I had some number of hops of some direction and length to get to the number I was trying to get to. Does that make sense?
I think it is so cool that we can word our goals like this, that we can say what number we're trying to get to and what is our starting position and are we preserving or are we reversing. It seems like the kind of thing that just gets skipped in the introduction of these things with our kids, but it makes such a big difference because those things can be used over and over and over, those same ideas. And so you always know where to start.
Yeah, and I think that what happens is we all learned this in first, second grade, third grade, wherever it was in our journey, right? That you learned this to some degree, and you may have learned it really well, or you may have learned it meh. But the chances are that you didn't see it over and over again to a point where you really understood it. Instead, we all saw it enough to where we kind of remembered the algorithm and we could do the computation enough that we could move on. And then we stopped kind of thinking about it. And now we're coming and we're teaching our children, right? And I think that we're all, by and large, a lot of us are going, but I want to do it a little bit differently. I want to do it a little bit better. And we didn't get to practice it enough. But guess what? Here we're going to talk about multiplication every single year. And so there's an opportunity to come back and revisit this, not just multiple times throughout the year, but every year. So your youngest students may just memorize positive times a positive is a positive and so forth. But your older students, right? Imagine if your sophomores, juniors, and seniors in high school have been doing this and they go, Oh, I get it now, right? That light bulb's going to come on because they're going to have this conversation over and over again instead of just going, I learned it, I memorized it, I'm moving on. You have the opportunity to come back so that that light bulb can actually come on for them. Now, for some kids, that light bulb might come on in fifth grade. Some it might be, in challenge 3. But the goal is that we're helping them to look for the patterns so that they see the light bulb, right? And by giving them language and the opportunity to revisit that, I'm hoping that that will happen. Um, just as you said that, Jill, about this language as well. I mean, this is a fun game that you could do with your kids, right? Pick a number, because it's so often we're asking them what the answer is. And so pick some number. So I don't know, Babs, give me a number.
6.
All right. So Babs said 6. And so then Jana, you give me another number.
-7.
-7. Okay. So now I could say to my kids, okay, everybody needs to come up with a T and a D to get from -6 to 7.
Did you mean from -7 to 6?
I did, yes.
Okay, I assumed so, but kind of matters, so.
It does. Um, and you might have the conversation, right? Are there 2 whole numbers that will get me from -7 to 6?
You mean like 2 and 4?
Yeah. Would 2 and 4 get me to 6? 2 times 4 wouldn't work, right?
No, wait, okay, right. I'm struggling with this. Hang on.
So it would be 9. So 3 times 3 and 3 is right? Is it 9?
Well, maybe you need 13,
That's 2.
which is
So
13
Jana
and
just
1.
Jana just said
only
if I'm
2.
here at -7 and I want to get here to 6, right? I've got to go 7 and 6. So I need to get to 13. So what are my whole number options to get 13?
1 and 13.
1 and 13 or
7 and
13
6.
and 1.
yeah, 13 and 1 or -1 and -13, right? Those would be my 2 pairs of numbers. That's the only ones for whole numbers. So then you could say if depending on your child, you could say, okay, the first person to find a fraction, right? Can anybody find a fraction that would get me there? Right? What if you had one fraction?
6
What if you
over
had 2
2?
fractions?
Would that work?
Say that again.
26 over 2?
20, yeah. So what if we wanted to have 2 factors?
Oh,
If
that you're adding.
26 times
1/2.
1/2, right? So notice how this is making us think differently, right? Instead of just moving forward in our progression. Now, for my youngest students, I'm just going to give them 2 numbers and say find the product, right? I'm not necessarily going to get here. But with our older students, and we're talking about, right, year after year, we're coming back and we're looking at multiplication. And yes, we're going to be looking at it algebraically and so forth. But here's a great, right, just a fun game. You're out sitting at the table, right? And you say, okay, Dad, give us a number. Everybody gets to pick, a number. And then everybody has to come up with a different way, right? And so there's like whoever goes first maybe gets the easy one, and whoever goes second. And then you start to see, can they see the pattern? So if they know that 26 and 1/2 works, what would be the next progression in that pattern?
39 and 3.
Ooh, I like that. 39 and a third, right? And then
42 times 1/4.
yes, right. So
52.
52 and a fourth,
times
right?
1/4.
So notice we're seeing this pattern now. So could we come up with an infinite number here? right? Because we're starting to see this pattern. If I add 13, I've got to divide by one more. Now we're starting to see that, right? Because I noticed, right, you guys were starting to see that. It might take our kids a little bit longer, but isn't that a great pattern for them to notice? Right? Isn't that a really great pattern for them to notice? So again, with our youngest students, do they need to know all of this? No, right? We're focusing on this. But since the question was asked, right, what are we starting at? The reason why we start at 0 is because it's kind of part of this whole equation, this whole idea, but we're saying every time we're just looking at this part, so that other part has to be 0.
And would it be true when we did addition and subtraction? I'm saying that the first number is the starting place, but really we could still say the starting place is 0.
And then
so you go to -3 plus -2. You move left 3 places, and you preserve the direction, and 2, 3.
All right. Any other questions on this slide?
Can you just remind, I'm sorry, I may have blanked out, what the T and the D stand for?
T is your counter. It's the number of direction vectors. So your direction vector in 1D would just be, +1, +3, +13, plus a half, whatever, right? However big my hops are. And T is my number of hops or my number of vectors. It's just a counter. And it can be any real number, right? It doesn't have to be a whole number. It could be I want half of my direction vector that was 26. Right? Or I could say I want 26 of my direction vector that's 1/2. In 1D, they're interchangeable. In other dimensions, they stop being interchangeable. So if I was to talk about, right, if I looked at this in 2 dimensions, right, I would have, this would become xy as my vector. And I would have some starting point that has 2. My t is still just a number, it's my scalar, but my direction vector is going to have the 2 parts as well. So let's say that my initial point was 1, 2, and my direction vector, let's say, was -1, 3, right? And my t was 2, then I would go left 1 up 2, 3. There's 1, left 1 up 2, 3, right? And this would be my new point here. Or in the case of lines, this would actually, right, all the points that are on that line would satisfy that equation. And we have other ways of talking about lines in 2 dimensions, but as soon as we get to 3 dimensions, this is the only way that I can talk about a line, is I'm going to have some starting point, right? So for lack of something else, right? Like my nose could be the starting point. And then I'm going to literally have a 3-dimensional vector, right? That's going to go, it's going to have a left, right, and up orientation, and it's going to go off of that point, right, however many times in whichever direction in order to describe a line. So that's in dimensions more than 2. This is the only way that we can describe lines. But if it's a pattern that's going to hold, we have to be able to see that it holds for the lower dimensions also. And we don't often do that. We talk about lines in other ways. So I like to show this. Hey, it works in 2D and it still works in 1D, except that here we're talking more about a point because the line is the line. So we're going to use it a little bit differently in order to find a point, right? Okay, did that help, Kristen? Veronica.
But I wanted to pause to see if that person got the answer that they were looking for. Okay. So with the examples that you've detailed out with words, the bottom 4 bullet points, could you just walk me through the language that you would use with number examples?
Sure. So I'm just going to erase what I have here. Okay. So let's say I had 4 times 3, right? And I would say, okay, well, there's my positive signs, right? We don't always write them, but for a beginning student, I would probably go ahead and make a little note that there's a positive there. And I would say, okay, so this is going to keep, I want 4, and it's going to be in the same direction. I'm going to preserve my direction. And what I'm preserving is to the right 3 units. And if I'm still working on visualizing this, I might draw a little number line. And I would say, okay, I need 1, 2, 3, 4 hops, right? Or 4 vectors or whatever I'm talking about, intervals. I kept the same direction, so I know that I'm going to the right, and that ends up at 12. If I had a positive times a negative, I would say, okay, this is a positive. So my direction, if I look at my direction first, I'm going to preserve my negative direction or my left. So whatever I end up with has to be negative. Because this says don't change it. This says you're going left. Then I do my numbers, 4 times 3, that's 12. If I had negative 4 times 3, again, I'd add in my little positive and I'd say, okay, this time I'm going to reverse my positive direction. So a reverse of the positive, which is right, is going to go left, which is going to be negative. 4 times 3 is 12. So I'm literally looking at each piece, my direction and my length separately. And then negative 4 times negative 3, this is telling me reverse my negative or my left. So that means I'm going to end up going right, which is positive, and 4 times 3 is 12.
So I was thinking about how we might use a deck of cards to give us lots of random practice with this, where the black would be positive and the red would be negative. So then whatever number you flip first
Yep.
is your first number talking, and then you look at the color to know if you're preserving or reversing, and then your second number that you flip, your second card, would tell you which direction is being preserved, right on the number line or left on the number line. Okay.
And I think for your learners that are struggling with this, the breaking it up and doing the 2 pieces separately might actually help them. All right. So let's just talk about the direction we're going to get. Then let's talk about how much, right? The multiplication part, the magnitude part. So instead of seeing all of it at once, if you say, okay, look, first just figure out the direction. And you could start there. If you have students who are working on multiplication with integers, you can just start with that, right? And just start. All we're going to do is figure out, am I going to get a positive or a negative? And just use this. And don't even worry about the 4 times 3 part. Just say, okay, we're going to start. And all I want you to do is tell me, all right, so I've got a red and a black. What's happening? I'm reversing my right. I'm going to get a negative, right? I'm reversing my negative. So I'm going to get a positive. Whatever the, right, however your cards, you could start there and then come back and say, okay, well, now we're going to do both parts. And sometimes for our students, breaking things up, right, so that there's just one skill we're practicing. It takes me back to my essentials days, right? The easy plus one. Like, don't try to practice every skill at once. Get comfortable with the skill and then add one more. And so when it comes to multiplying with integers, just figuring out, right, what direction is my answer going to be, that's a task all in of its own.
Thank you. That's very helpful. I have a student that's right here. So thank you.
Yay. All right. So now I just want to remind us that when we have our place value, that there's the hidden addition. We've talked about this now for a couple of weeks, the additive expansion, the multiplicative expansion, the exponential expansion, being able to take a number and expand it, right? We're not going to do this forever, but this really is going to help our students, I think, to understand, or maybe it's just for us, and then you don't make your students do this. But this is what helps us to understand why we only need to know 0 times 0 through 9 times 9. Okay, because I can expand this, and the highest number I'm going to have, right, for any of these, right, once I write it this way, is going to be in decimal, it's going to be base 10. I'm sorry, in decimal, which is base 10, it's going to be 9, is the highest digit I'm ever going to have. Right? That's it. So if I can multiply 9 times 9, and then we do trades like we did with the addition, right? But if I can memorize 9 times 9, then that's what I need, right? To understand this. So let's go ahead and look here and just review the distributive law, right? So all of our students, right, from our youngest ones are practicing the distributive law, that A times the quantity B plus C is AB plus AC. If you have students who are more linguists than symbolic, the words that you can put to this is that the product of a number and a sum is equal to the sum of the products of the number and each term, right? For some students, hearing those words may be more helpful than just reading the symbols. That's all the symbols are telling us. Right, when we look at this and we see this in a more abstract way, right, it's important for us as parents, as the teachers, to remember that A, B, and C can be single numbers, literals, expressions. They can really almost be anything. And so I've given you some examples here that I can say that it's 3 times 4 plus 5, 3 times 4 plus 5i, 3 times x plus 5. Or I could have two binomials, x plus 3 times x plus 5, or a binomial and a trinomial, right? I can have any number of things that are inside my parentheses, but when I look at it, the first factor is going to be my A, and then like this could be my B, and this is my C, right? And it all works the same way. So when we think all of these different multiplication examples all come back to the distributive law. Now, I want to point out that everything below that squiggly line is where the distributive law is really, really helpful, because I cannot add within my parentheses. Here, I can. So if I was looking at my order of operations, most of us would say, well, this is the same thing as 3 times 9, which is 27. Right? You're going to see that Lee practices this a lot so that students see that 3 times 4 plus 3 times 5 is 12 plus 15 is 27, so that it demonstrates the truth. So it is true when we just have numbers. It is oftentimes not as powerful, because I could simplify within my parentheses and then multiply. But as soon as I can't simplify within those parentheses, that's where the distributive law becomes really powerful. And then we're going to look in a minute and see how we use the distributive law, but it's kind of hidden when we're dealing with big numbers. Now, I think I forgot to make a slide, so I may have a slide for this, but I don't think I do. I did want to point out that this fact here with numbers is a way that people can use mental math tricks, right, when they're trying to become really fast at mental computation. Because if I said 2 times 17, it may be a quick product for you, but I can break that up into 2 times 15 plus 2, right? And I might go, oh, well, 2 times 15, that's 30, and 2 times 2 is 4, it's 34. So I can take this number and I can break it up however I want to into a sum, right? And that's one of the tricks that those mental math people, when they're going really fast and they're looking for fast ways to do mental math, is that they recognize that if I have some number here, I can break it up into pieces, and I can break it up in, like we're going to look in a minute, we're going to look at, right, our expansions of our base 10 numbers, but it doesn't have to be that way. When we're doing it to be quick, we can break it up into any way that we want to, right? So very powerful. I think that the distributive law is the unsung hero of mathematics, or at least of arithmetic, and often overlooked. All right, so now let's take a look here at beyond the digits, right? So we talked about memorizing 0 times 0 through 9 times 9. And if we have anything that's beyond those digits, so 2-digit numbers, 3-digit numbers, this is what's happening. What I'm about to go through with you is really ugly. I'm just going to put it out there that it's going to look ugly at some point to you, because it's the underlying idea of what's happening when we multiply. This is not how I suggest that you have your children multiply all the time. But I want to show you as parents this underlying, the underpinning of multiplication. What is actually happening, even though we hide it in different arrangements, this is what's actually happening, so that you can be convinced that all you need are 0 times 0 through 9 times 9 and the distributive law, and you can multiply anything. So I say, first, understand place value, which means that I look at my numbers and I can recognize that 34 is 30 plus 4. And in this case, I'm leaving it in its sort of additive expansion. Then I can use the distributive law. Instead of 2 times 34, I recognize that 2 times 30 plus 2 times 4 is the same thing. And then I'm going to think about what are my units. And so here you can see that I did at this stage, and I could have done it sooner, but at this stage, all right, I broke this out so that I could see my units. So my units in this case are tens, and my units in this case are ones. So now I don't need to worry about my units yet. All I need to worry about is what's in red, 2 times 3 and 2 times 4. So 2 times 3 is 6, tens, and 8 ones. That's my 60 plus 8, or 68, right? Again, I just want you to see the underlying idea behind what we're doing. I am not suggesting that you need to make your children do this every time they multiply, right? Now, some of your students might be really interested. This might help the light bulbs go on, because they go, oh, that's why what we're doing. But my goal is really to help you as parents see that, and then you can determine how granular you want to go with your students. Any questions from this example?
Why did you choose 4 times 1 instead of just saying 4 is the unit?
Well, because in my place value, going back to place value, remember I would have, this would be my 0th power, which is 1. This is my first power, which is 10. My second power, which is 100. So when I have 4 here, it's really 4 ones.
So then why wouldn't you go further and say 3 times 10 times 1?
Well, because again, so this is where I'm going back to, that these were my ones, these were my tens.
Oh, gotcha.
So I'm just, right, so I'm just pulling it out from place value, so I can say, okay, I'm just working in my place. I'm going to look at my ones. Now I'm going to look at my tens and my hundreds and so forth.
So it's based on the number you started with.
Yes.
Okay.
Yes. Which in the next example, I do a little bit better of showing that. So let's take a look here. And this is the start of the problem, and the next slide has the rest of it. And this is where I'm going to say it does kind of look ugly, right? But I just want to help us all go, this is all we're doing. And I'm writing out every single step that usually we don't write out, but I just want you to be able to see where it all fits in. So in this case, I've put units on here of centimeters so you can just kind of see where they go. So let's say I have 23 centimeters and 50 centimeters. The first thing is I'm going to show that hidden multiplication between my number and my centimeters. So now when I look at the product of them, I can see that I can rearrange, right? Through the commutative law, I can rearrange so that my 23 and my 50 are together and my centimeters are together, right? That's why the commutative law matters, because it means I could just move all of these numbers around. Then the associative law says, okay, now I can multiply my numbers and I can multiply my units. And I'm going to look in a minute at using the distributive law for the numbers. But because I have like units in this case, and I'm going to show you an example in a minute where I don't have like units. Right, here's like units. So I'm going to use my exponent because it is centimeters times centimeters. This is a big difference, right? And this is where writing out those hidden steps, especially for you as parents, if it hasn't clicked yet, keep writing them out. When we talked about addition, right? If I had 23 centimeters plus 50 centimeters, notice the difference that I would undistribute my centimeters and I would add my numbers to get 73 centimeters, right? It's still linear. I basically said I took my 23 and I've added my 50 centimeters, and now my length is 73 centimeters. When I'm multiplying, if I have 23 centimeters times my 50 centimeters, notice what I end up with are centimeters squared, right? I'm not putting them next to each other now. I'm giving dimensions, so it becomes two-dimensional. And so my units change to centimeters squared. And we see this here in the arithmetic, right? That I have centimeters times centimeters because I'm multiplying, I'm not adding.
Could you remind me of the associative law? I got the commutative and the distributive. What's the associative?
The associative is this part that says I can group them differently, right? And so I can take my numbers and I can multiply them together and I can multiply my units together and then I can multiply those two products together. That's the associative law. It says that the way I group my multiplication doesn't matter.
Is that the A times B equals B times A? No, that's commutative.
It's the ABC equals AB times C. That's the associative law. This is the A plus B equals B plus A.
Got it. Okay, thank you.
And we have our students memorizing these, and we see it more clearly in algebra, but in arithmetic, a lot of times it kind of gets hidden. And so I really wanted to be clear with you on this call that this is where those laws matter, right? Because these are the laws that say I can do all of this rearranging and multiplying. So the next slide, we're going to look at multiplying 23 times 50. Any questions on this slide? Okay. So again,
Hey, Kirsty, there was a
yeah.
question in the chat. It said, why is it centimeters squared instead of 2 centimeters?
Well, because I'm doing centimeters times centimeters, right? the exponent when I have centimeters times centimeters, that's going to be my repeated multiplication, which is exponentiation. So this 2 right here tells me that I have 2 factors of centimeters, which is centimeters times centimeters. If I had 1 centimeter plus 1 centimeter, that would be 2 centimeters. Right? So if I'm adding my centimeters, that's where I would stay in centimeters. As soon as I'm multiplying, that's where I'm finding the product, and I have to use that exponentiation to show that I have 2 factors now and not just 2 addends. Does that help? Not sure who asked that, but does that help?
She said thank you, so I think, Laura, are you
Okay.
good with that one? Okay.
Well, I think I got stuck on at the very beginning. It says 23 centimeters equals 23 times centimeters, and 50 centimeters equals 50 times centimeters. I thought you were adding, and it took me a couple of minutes because of that word and to figure out that you were only multiplying. So I wonder if that might have made it. I thought you were saying 23 times centimeters plus 50 times centimeters because of that word and. And so I caught up eventually, but I could see why would it be centimeters squared as opposed to 2 times centimeters,
Okay. Well, good. All right. So again, this is showing every single step, I think, because I would rather you see all the steps than me skip something. So we've got our 23 centimeters times 50 centimeters, and we break it out here. Turn my pen on. Right, so we've done this part here, and we got down to here to centimeters. Now, as I look at this, because I have 50, I could make this 50 plus 0 so I could see my ones, but I chose just to leave this as 50 for now. And what I see is that I'm going to distribute I'm going to distribute backwards. It's the same thing, it's just I didn't rewrite my problem first. So I see that I have 20 times 50 and 3 times 50. There's my distributive law. Now I look at this and I go, okay, I'm going to now write this out in terms of place value. So I have 20 is 2 tens, 50 is 5 tens, 3 here I have 3, it's ones, and I didn't write that, so I obviously didn't write all my steps. And then my 5 tens. Right. So this I could have put in here a 3 times 1 to help us remember that those were 3 ones. Now, again, I'm going to look at I rearranged this so that I have, and I guess I didn't write every step. I'm going to be honest with you. I had more steps and I must have taken some out. So I could have rewritten this as 2 times 5 times 10 times 10. Right? And so my 2 times 5 becomes my 10. My 10 times 10 becomes 10 squared. Right? Just like my centimeters became centimeters squared, 10 times 10 is 10 squared. So here I've got my 3 times 5, so that becomes my 15, and then my units are the tens. Now, because I have 2 times 5 became 10, I can multiply again and I get 10 cubed, and so I have 1 times 10 cubed. My 15 I can write as 10 plus 5, and now I see that I'm going to have a 10 squared and a 5 times 10. And so I end up with my 1 times 10 cubed. Here's my 1 times 10 squared. Here's my 5 times 10. And I didn't have any ones because I had this 10 in there. And so notice this is my thousands, my hundreds, my tens, and then I have no ones. So I have 0 ones. And that's how I get to my number. This is not how I expect you to teach multiplication to your students, right? This is the underlying nature of what we're doing. This is why multiplication works, is we just keep applying the distributive law and understanding place value. That's all we're doing is the distributive law and place value in order to do this. Next week, we're going to take a look at all these different arrangements that hide this, right? And it's going to be hidden, and we're all going to go, oh, that's the multiplication I remember. But I wanted to show you this so you could see why those arrangements work. Because all those arrangements are doing are helping you do your distributions, right? When we write it out like this, it's really ugly to see all of it. So that's what we're going to take a look at next week. So this week, I really wanted to show you why what we do next week works. So in the meantime, I would suggest that you use dice or cards to create random numbers. Practice being able to write the 3 expansions, right? Just practice writing your numbers as hundreds, tens, and ones, and recognizing how to do those expansions, right? So that you're really emphasizing place value and recognizing the units. Practice the commutative law, practice the associative law, and then you can practice, right, combining non-numeric units, like centimeters squared. Or here's an example, right? So just do things like this. So these are 2 random numbers, right? And so you, again, without ever actually doing the multiplication, just practice expanding. So you have, we're short on time, so I'm going to do the talking, right? So 20 feet is the same as 20 plus 0, right, times feet, or 2 tens plus 0 ones, or 2 times the first power of 10 plus 0 times the 0th power of 10 feet, right? So you can just practice writing those expansions even with small numbers. With 27, it might be easier to see, there's my feet, that I have 20 plus 7 feet, which is 2 tens plus 7 ones feet, which is 2 times the first power of 10 plus 7 times the 0th power of 10 feet. And then ask your students, right? So what's my place value? Well, it's ones or 0th power of 10s and 10s, right? Ones and 10s. Those are my units for my place value. Then you could say, okay, let's look at the commutative law, right? So if I took 20 feet times 27 pounds, right? Can you rearrange it so your numbers are next to each other? Sure. So that's 20 times 27 times feet times pounds. Now let's practice the associative law. Put parentheses around your numbers and your units. Right? That's my associative law. And now look at your non-numeric units. Is there any other way to combine them? In this case, it's not, right? Feet times pounds just becomes foot pounds. That's what they would call it. It's right? And so we can have kind of weird units like that just by multiplying them together. Had they both been feet, I could practice being feet squared. Had I had 3 different things that I was multiplying, maybe I would have had meters cubed, right? It doesn't, just practicing combining those parts of the units, or omit that entirely and just worry about the number part, right? And just do the number part and don't even worry about the units. So I'm giving you sort of the bigger example, and you can scale that back and just do the number part. All right, and then practice doing 20 times 27 or 27 times 20. If I only have two numbers, I can't really look at the associative law. You really need three or more for the associative law. But that's what I would do, right? Is just this part. And don't even worry about the multiplication of the number part. So that your students are going to get to see, right, to remember that all of these parts go into what they're doing. Again, I mentioned this earlier, right? If I have a scalar times a length, right? Scalar, no units other than one, times a length, what are my units going to be? So here's a case, if I have three
That length.
5 centimeter lengths, it's going to be a length, right? I stay in the same dimension. Here, if I have, here's my 5 centimeters, and I have, right, 3 centimeters this way, pretend they're equal, right? What kind of unit do I have?
Centimeter squared.
Centimeters squared. And if I was to take that now and expand it out this way, which is not drawn well, but pretend that it is, right? So I have my 3 centimeters and my 5 centimeters and my 2 centimeters. I'm going to end up with what kind of unit?
Cubic.
Centimeters cubed.
Centimeters cubed. So for your older students, as you're practicing the dimensions, as you're looking at this and thinking about measurements, even if you're out and about, right, help them to see that there's a difference, right? When I start multiplying my units, I start changing my dimensions, which is a different activity to just scaling a dimension. All right. So next week, multiplication will look much more familiar because we're going to hide all of that ugliness, and we're going to look at, right, when we multiply, trying to see, yes, here's our algorithm that's really familiar to us, but pointing out where what we looked at this week, that underpinning of multiplication, where does that get hidden? And then how can you help your students to make connections between the two, right? So that as they're gaining in familiarity, right, the goal is that, yes, we all are going to be quicker, right, once we kind of know what the algorithm is that works for us. But our understanding, right, we want to be able to ask good questions to help our students to see what's happening underneath. So not in your first year of the math map, not necessarily in your second year, but as you continue to revisit multiplication, that's my goal, is that you feel equipped to have those conversations with your students so that you can help them to see, right, why does it make sense? All of these different ways that people say, you know, the Japanese method or the box method, right? All these different methods of multiplication, why are they all doing the same thing? Because it's what we talked about today. So hopefully I haven't scared anybody off, because it was kind of ugly, I'm not going to lie. And you'll come back next week and see more familiar multiplication. And as always, I'll hang out for a minute. I did want to share something with you. I was at a conference last week, the Association of Christians in the Mathematical Sciences, and we had some fantastic speakers. Ty Dene spoke on the second evening, and this was not at our event. This was the same talk recorded elsewhere. I would really encourage you to listen to it, because it is a story of God's faithfulness to somebody who wanted to know God more than anything. And he drew her into mathematics as an older student. So she did not grow up loving mathematics. She did not think she was a math person. She did not come from a family of mathematicians. And God just really drew her to love math and then be faithful to her. And so it's really just her testimony of God's faithfulness. And it was really beautiful, and really encouraging. So I just wanted to share that with anybody that may be going, okay, do we have to be naturally mathematically gifted at 3 to pursue mathematics? And the answer is no. And I think that you'll all be encouraged by her, because she was a just fantastic speaker with just an amazing story, and all she wanted to do is give glory to God. So well worth the watch. Any questions?
I have a somewhat telling question. What is the name of this series, this book club series for the summer? I know I haven't been as engaged as normal.
We haven't. Babs called it our arithmetic boot camp. Um, Lee said it was kind of a frequently asked questions, but it really is a focus on arithmetic and the underpinnings of arithmetic, and trying to build kind of let's call it the underpinnings of arithmetic, right? We've kind of done a deep dive into why arithmetic works the way that it does.
Okay. I recently had a conversation with someone who said that as a challenge for a director, she read the first 3 chapters of Calculus for All of Us and got a deep conviction that she had not been teaching her children math. And they all went through Saxon and they were all good students of math. But she was like, I did not teach my children how to think mathematically. Maybe she said she was teaching them arithmetic and not math. I can't remember the terms. But that has me thinking that this whole conversation or demonstration reminded me of that, because I never thought through the process of what I was actually doing when I was completing accurately the algorithms that had been taught to me around multiplication. So I am not, I'm not, I'm not, I'm with you when I'm not sure I'll put this in front of my kids, but it is a very interesting way to understand what we kind of already knew but didn't know that we were doing.
I think that's why I always try to say, right, this is geared to you as parents, not as this is how you should teach, but I want you to feel like you are starting to see the patterns so that you can ask good questions and guide your students to see the patterns. And if you think, for most of us that went to a traditional school, we may have had fantastic teachers. The reality is that when people say, I'm going to go into teaching, if they have a strong math or science background, or they're really good writers, right? If they have a strong subject focus, they're going to be guided to teach high school, right? If they don't have a strong focus, especially in the maths and sciences, right, then they may be guided a little bit more towards elementary school. So you end up with teachers in elementary school that probably, and it's changing now. Teacher education maybe is changing a little bit. I talked to some people last week who are really passionate about trying to help elementary educators have more of this. But historically, our elementary educators really were never asked to think deeply about things. They knew algorithms and they taught algorithms, right? And then you really don't come back and revisit multiplication once you have that skill. It's assumed that you can do it, right? And so that's why I'm encouraging us as parents to go back and to see the patterns. I really saw it right when the Furor over Common Core came out, and people were like, well, there's a new way of multiplying. Well, it wasn't really, because multiplying has always just been the distributive law. That's all it is. If you're beyond the digits, it's distributive law. It was a new arrangement. And we as classicalists have the language, right? That we can sit there and we can go, the authority for a multiplication is the distributive law. For every single multiplication problem, and you could make the argument that you could even do it for single digit multiplication, but that just collapses down into the repeated addition, right? But the distributive law is our authority for every single multiplication problem. But we can arrange it in a whole bunch of different ways. And so we have a language that allows us to see that, where people in the traditional, right, realm really don't have the language. And so what happens is everybody goes, this is totally different. And so we're trying to be clear, like, hey, there's all these different arrangements. It's not different. It's still the same authority, the distributive law. And so part 2 next week will hopefully help us to see that. So definitely come back.
Amazing. Thank you.
Well, thank you. I appreciate all of you guys being here. Well, as always, I'll stay on for a couple of minutes if anybody has questions, or if not, I will see you next week.
All right. See you later. Thanks so much.